Hi everyone, welcome back. My name is Ananth, and today we're going to be talking about reinforcement learning. And this will be the first video in a short course mirroring the content taught in CMSC848N by Dr. Farong Huang. So at a high level, all RL problems deal with three major components, that being the agent, environment, and transition dynamics. The agent refers to the autonomous system we're trying to train. The environment is the set of constraints that agent abides to. And the transition dynamics has to do with state, where the agent is currently positioned, action, what the agent can do, and reward, an immediate scalar feedback for a given action state pair. So for the rest of the lesson, we're going to be using the snake game as our example, shown here on the left, where the snake will be our agent. The n by n grid is our environment. The state is where the snake is positioned. The actions are up, down, right, left. And the reward can be +1 for survival, -1 for death. Another thing we're going to define is the Markov property, which states that all future states only depend on the current state. Next, we'll consider some foundational formulas that will enable reinforcement learning. First, we have the value function, which is the expectation of your cumulative reward, assuming you start in a state S. In the snake game, this is your expected score if you start in a position S, say 0, 0, and follow your optimal policy pi thereafter. Then we have the action value function, which refers to the expected cumulative reward, assuming you start in a state S and follow an action A. Next, we string these two together to define the Bellman optimality equations, which say that your optimal value given a state S is the expectation of your current reward plus the discounted value of the next state. And the optimal action value function is the expectation of your current reward plus a discounted value of your next action state pair. And together in the snake game, we can imagine that these functions define our optimal strategy, which will therefore lead to the longest survival. Now we can apply these functions in some popular RL-based algorithms. We have dynamic programming, Monte Carlo simulation, and temporal difference strategies. And the main differentiator between these has to do with bootstrapping, which is waiting for a full episode to end in order to update your policy, and knowledge of environment dynamics, which refers to the reward for any given state action pair. In dynamic programming, we do bootstrapping, but we do require full knowledge of the environment dynamics to do so. In Monte Carlo, we cannot bootstrap, but we don't need full environment knowledge. And in temporal difference strategies, we combine the best of both worlds, where we bootstrap and we do not need to know all of the environment's dynamics. In dynamic programming, we're following a loop of value iteration followed by policy iteration. And you can imagine it's not sample-based, and we're summing over all possible actions at any given state. And this is not feasible for our snake example since we don't have the full reward or transition model for any given state. In Monte Carlo simulations, we're following our policy pi for a full run, and they're updating our values after that episode. In the snake game, you can imagine we have a certain strategy, and from start to finish, we're going to implement the strategy. Afterwards, we're going to check what worked, what didn't, and update our policy accordingly. And in temporal difference learning, we implement a strategy that updates our value at each step, where we sum the observed value with the estimated value of the next step. In SARSA, our first on-policy TED algorithm, standing for state action, reward state action, we're going to implement exactly what we saw in the previous slide. Right here, you can see the update where we're updating the next step of the estimated value for that next step using Q of S prime A prime. And this follows the current policy that we defined already. Contrastingly, in Q-learning, we implement an off-policy strategy that will choose the action greedily. So despite what your policy may indicate, so your previous Q values, we're going to use the maximum of those values for choosing A prime. Next, we'll discuss some scaling strategies for RL so that we can practically apply these algorithms. First, we have function approximation, which has to do with replacing lookup tables. For example, if you're looking for the Q value of a certain state action pair with parameterized functions. And our goal in this case is to minimize mean squared value error. So for our snake example, you can imagine that we replace or we estimate a snake state using a neural network. Next, we have the policy gradient, which allows us to directly learn policy parameters via gradient ascent on the expected return. So using the policy gradient theorem that we see here, we can update parameters for our policy directly to increase return. Now we'll discuss the actor-critic architecture, which is the bridge between value-based methods and the policy gradient strategy. So the actor is aimed at improving our current policy pie, and the critic is focused on evaluating that pie. So the critic's goal is to reduce variance in the policy gradient updates by using the temporal difference errors to produce an advantage for a certain step. And the actor will take this feedback and apply policy gradient theorem to directly update the parameters in pi based on this advantage. Now, finally, to recap everything we've covered, we talked about the Bellman optimality functions, which are the basis for reinforcement learning. We covered dynamic programming, Monte Carlo simulation, and temporal difference learning. For scaling, we learned that lookup tables are not the way to go when your parameters really increase or you have continuous functions. So we introduced function approximation and policy gradient. And finally, we discussed the advanced architecture of the actor critic, which enables the value-based functions we learned earlier with the policy gradient that we learned in the latter half. And always remember, when struggling with reinforcement learning problems, it's always very helpful to frame it in the snake game perspective. There's almost always a parallel you can make, and it really simplifies things to understand more complex topics. That's all for today, and I'll see you guys in the next one.